Hello all and welcome to this video. Today we are going to go over the May 2019 paper for Unit 1, okay, Mechanics and Materials. And this is from the advanced subsidiary level, so the year 12 students. What's special about this paper is that I believe this was the first paper that was based on the new spec, which is not much different from the old one, but nevertheless, I think it was the first. And I think that year they also released a version that was based, that was also taken on May 2019 with the old spec. Maybe we will go over that at some point in the future, but let's dive in, okay? Section A, question 1. Quantities in physics are classified as either vectors or scalars. Which of the following units can only be used for a scalar quantity? Okay, so meters per second is velocity or speed. Okay, speed is a scalar quantity, but velocity is a vector quantity, so no. Meters per second squared is acceleration, which is a vector. Kilograms times meters per second squared is, which unit is that, guys? Take a moment to think about it. It's the Newton, okay? And therefore, the last one is the only remaining one, so you can actually select it by the process of elimination, but we can immediately recognize that that's density, which is scalar. Okay, it doesn't have a direction. It doesn't make sense for density to have a direction. All right, question 2. Once in orbit above the Earth's atmosphere, the engineers on a space rocket, the engines, not the engineers, okay, on a space rocket are switched off. Which row of the table correctly states the resulting motion of the rocket and the law explaining this motion? Okay, so what does orbit mean? Okay, if you have the Earth and this is your satellite, which is a point compared to the Earth, it's going around. This is something that you eventually learn in Unit, I think, 4, right? But okay, when the satellite is in orbit, the velocity is tangential to the circle, right? So the velocity always changes direction, okay? So that's the key. So the velocity is not uniform because only the magnitude is constant. So we have changing velocity. So immediately eliminate options A and B, right? And then option C says that the explanation for the changing velocity is Newton's second law, which is correct, right? Because option D says Newton's third law, that's absurd. No, because Newton's third law is related to action and reaction. I mean, like if a body exerts a force on another body, then the other body also exerts the same force in the opposite direction. So no. So C is the only correct option. All right, question 3. A sphere of weight 2.5 newtons floats in water with 1/2 of its volume beneath the surface. A force F is applied to the sphere, completely immersing it in the water as shown. Okay, so if we focus on this, the left scheme, we see that we have two forces, up thrust and the weight. So up thrust is equal to the weight, so it's 2.5 newtons, but we know that up thrust is the density of water times G times the displaced volume, which is the half of the volume of the sphere, right? Now, if we move over to the second drawing there, I mean the second picture, whatever, we have the weight still, right? Now we have a new up thrust, and we also have the force, and we have a new up thrust, right? Which is equal to the density times G times the whole volume, right? Because the whole volume is displaced. But since we know that rho times G times the half the volume is 2.5 newtons, we know that this is 5 newtons, right? So 5 newtons must equal the weight, which is 2.5 newtons, plus the force. So we immediately see that the force is 2.5 newtons, and the correct answer is B, right? Yes. Okay, Question 4. A ball rolls off a table with a horizontal velocity of 1.2 meters per second. The ball takes 0.9 seconds to reach the ground and lands at distance s from the table as shown. Which of the following expressions should be used to determine the value of s in meters? Okay, s is related to the horizontal motion of the ball, right? And I have a video analyzing all these motions. Maybe I'm gonna link the video in the description, but in general, s in the x direction, we can put the subscript, is v in the x direction times t plus 1/2 times the acceleration in the x direction times t squared. There is no acceleration in the x direction, so it's so the distance is simply v times t. V is 1.2, t is 0.9. So we have to search for this option. It's option B. Okay, I hope this makes sense. Let's move on. A sample of seawater is collected using a beaker. The sample contains some particles of sand which settle at the bottom of the beaker. Which of the following would result in a decrease in the time taken for the sand to settle? Okay, so as the sand moves through the water, I can use a clean page to demonstrate. Okay, so this is the beaker, I guess, with the water. Can erase this. Okay, and maybe this is the sand particle. Okay, that sinks in the bottom of the beaker. So it experiences some upthrust, and the drag force, okay, F drag, and it also experiences the weight. I think they say that we can ignore the upthrust. Do they say that? No, they don't. Okay. Okay, which of the following will result in a decrease in the time taken? Okay, so the drag force is the Stokes force, so 6 pi times eta, which is the viscosity, times the radius of the sand, times the velocity. Okay, so let's read. Smaller particles means, let me see, means a smaller radius, so smaller drag force. That sounds plausible actually, but let's read the other ones. Lower temperature of the seawater will result in lower viscosity. So that sounds plausible too. Okay, now I'm confused. Will result in a decrease in the time taken. Smaller terminal velocity of sand particles. No, it means it's gonna sink. It's gonna take lots of time to sink. And the lower viscosity of the seawater. Okay, they mentioned it explicitly. So D is actually the correct answer, right? So if we use smaller particles, they will have a smaller terminal velocity. Okay, so option A is not correct actually, now that I think about it, because this terminal velocity would be small and it will take a long time. Then B, if the temperature is lower, sorry, I didn't read that. Lower temperatures means higher viscosity, so it's going to take longer. So yeah, D is the correct answer, because if we have a lower viscosity, then the drag force will be reduced. So D is the correct answer. I'm sorry for confusing you. Okay, let's go to question 6. A graph of stress sigma against strain epsilon up to the breaking point is drawn for 4 samples of wire A, B, C, and D. Which sample of wire has both a low elastic limit and a large region of plastic deformation? Okay, B and D do not have a large region of plastic deformation. Okay, so this is the region of plastic deformation. Okay, which means that we increase the stress, but it doesn't break, it keeps extending. This is what it means to have plastic deformation. Okay, now let me erase this. Now we are looking for large plastic deformation and low elastic limit. Okay, so the elastic limit is the limit where Hooke's law applies pretty much, okay, where we have a linear dependence. So this is true for C, right? So this is the elastic limit and this is the elastic limit for C, okay? So that's the elastic limit, so C is the correct answer. Right. 7. A water pump causes 200 grams of water to be ejected from the nozzle of a garden hose each second at the velocity of 3 meters per second. Which of the following expressions could be used to determine the the minimum output power in watts required from the pump? Okay, so for watts we need the power actually. So power is energy per time. Okay, so we are given so energy in this case is the kinetic energy of the water, which is 1/2 mv squared, right, over time. We are not given time explicitly, but we are given the fact that 200 grams of water are ejected each second, okay? So we are actually given this sentence translates to mass per time, which is 200 grams per second, okay? And the velocity is given explicitly in 3 meters per second squared. So if we plug in numbers, we find, let me see, 1/2, then mass per time, this quantity is 200, right? Okay, 200, which should be converted to kilograms there, so that we have watts, right? So 0.2 kilograms, right, per second. And then V is simply 3 squared. So the correct answer is B, right? Yes. Okay, 8. A model rocket is launched and moves vertically upwards upwards while still burning fuel to give a constant upwards thrust. The fuel runs out and the rocket reaches the maximum height at time t before falling back to the ground. Which of the following graphs could show how the acceleration A of the rocket varies with time t if the decrease in mass as the fuel burns is neglected? So basically they are telling us that okay, when it falls, okay, all the graphs could be correct, because when it falls the acceleration is minus g, right? The acceleration due to gravity. Now it moves with a constant upwards thrust, which means that the acceleration is constant, right? So options A and B are wrong because the acceleration is constant. And the acceleration is given by, we have, when the rocket moves up, actually let me use a clean page. So if this is the rocket, does this look like a rocket? Okay, something like that. Okay. All right. So it experiences upthrust, which is constant, and weight and drag force. Okay, something like that. So upthrust minus drag minus the weight is ma. But okay, they tell us actually ma is not the correct equation to use, but this is A-level physics, is not university level physics. So they ask us to assume that the mass of the rocket is constant, okay? Which is not because it loses fuel, right? It burns fuel. But anyway, so A is upthrust minus D minus weight over m, so it's constant, right? Because upthrust is constant, weight is constant, and drag can be taken as approximately constant, I guess. Do they ask us to ignore the the drag force? They don't. Anyway, so as it moves up, at some point, okay, is it C or D? So at time t, the fuel runs out. okay, from the time it runs out, it will start falling backwards, right? So C is the correct answer because T means that the fuel runs out and it keeps moving up pretty much, which doesn't make sense. So C is the correct answer. Let me see what the mark scheme says. So D is not the correct answer as it has a small region of plus. Oh, wait, sorry, I'm reading the wrong problem. I want to read the mark scheme for this one because I'm a little bit unsure. So A and B are obviously wrong. So for A, they say A is not the correct answer because the acceleration should be constant as there is a constant upwards thrust from the fuel. Okay, this is what we explained anyway, so that's correct. B is the same case. Then D is not the correct answer because the acceleration becomes negative as the fuel runs out and not at the maximum height. Okay, so this tells you that okay, A, but they say that C is the correct answer as the acceleration is positive while the fuel is still burning. It then becomes negative while still traveling upwards as the only forces acting on it are downwards, weight and drag. Okay, I see. All right, so let's move on to question 9. Okay, for this one I had a little bit of trouble until I saw what I was doing wrong. So a student walked 12 kilometers on a bearing of 135 degrees and then walked 20 kilometers on a bearing of 340 degrees as shown. Which of the following could represent the final displacement of the student from his starting point? So the best way to see it is, okay, let me remind myself how I did this. Okay, the correct answer is B. But okay, I had trouble explaining it to myself earlier when I was solving this. So the way to explain this is to go here in this situation, right? So basically, or maybe here. Okay, let's try to explain it. So the student moves 12 kilometers south under 135 degrees, and then starts moving north and west at the 340 degrees. So if we come here and draw the north, so the true north will be this one, right? Oops. So let's try to draw it again. Okay, that's the north. And then it says that it travels 340 by 340 degrees, which means that this angle is 20 degrees, right? So so let me think. So 20 degrees would be, okay, a very small angle that will look like this. Okay, this is what I'm trying to draw. Okay, there. So this will be 20 degrees because it starts moving in that direction. Therefore, the displacement will be this vector, right? So he starts there and he ends there, so that's the displacement. It looks straight, but it's not, so it's this one, okay? So the correct answer is B. I hope this makes sense. And I always had trouble with geometry of this kind sometimes. I mean, since I was a student. So let's move on. So question 10. A lift moves upwards from rest with an acceleration A. A student of mass 70 kilograms standing in the lift exerts a force of 800 newtons on the floor of the lift. Which of the following expressions could be used to determine A? So if this is the lift and this is the student, the weight is m times g, and then there is the normal force, which is 800 newtons as it's stated, right? So n minus mg it moves up, so the acceleration is up. So n minus mg is m times a, and the reason is because the positive direction is taken as upwards. So 800 minus 70 kilograms times g is 70 kilograms times a, and the correct answer is C. Okay, that's the answer because it moves upwards. All right, short break before we move to section B. This test, I think, was one of the hardest tests I've seen at the A levels. I don't know why, and it's just unit 1, so I don't know. I'm gonna go over unit 2 and unit 3 eventually from 2019 and get a feeling for these tests, but maybe because it was the first time the new spec was introduced, they experimented with new ideas or something. So, but I think it was hard. So let's move on to question 11. It's a conceptual question. A child is standing on a skateboard and both are stationary. The child throws a ball forward at high velocity, and the child and the skateboard move backwards at a lower velocity. Explain in terms of momentum why the child and the skateboard move backwards at a lower velocity. Okay, so this is a conceptual question. So first of all, you have to observe that, okay, this is the situation before and this is the situation after. And before, both the kid plus skateboard system and the ball are at rest. So the initial, so this is the first thing we have to write. The initial momentum of the child skateboard ball is 0. Okay, and I'm gonna digress a little bit and remind you that, okay, this is a 4-mark question. I mean, you can see it down there. Okay, which means that first of all, it should take you about 4 minutes to answer, and the second thing is that in conceptual types of questions, usually if it takes 4 marks, you have to provide 3 to 4 points. Okay, so the first one in the description of this thing is to say that the initial momentum is 0. Okay, so if we call the P, the momentum of the ball, must equal the P, the momentum of the skateboard, I hope you can read this, plus child. Okay, so the momentum of the ball must equal the momentum of the skateboard plus child system after the ball is thrown. Okay, so this is the conservation of momentum pretty much. Okay, so the momentum before must equal the momentum after, right? So 2 points so far. The third point we can raise is that the mass of the ball times the velocity of the ball must equal the mass of the child plus skateboard times the velocity of the child plus skateboard. I'm writing it with tiny letters because this is supposed to be a subscript. Okay, and okay, the momentum must be equal, and maybe we should put a parenthesis there to make it clear that this is no, it's confusing. Let's name this, I'm sorry, let's name this MSVS. Okay, and it's supposed to be the skateboard. Okay, so the momentum must be equal and in opposite directions. Okay, and just to be safe, we can actually denote it here that this is M skateboard V skateboard, and this is M ball V ball. Okay, now since the mass of the ball is smaller than the mass of the skateboard, then V of the skateboard, which is actually equal to M of the ball, V of the ball, over the mass of the skateboard, which is a large number, then since this is the mass of the ball is smaller than the mass of the skateboard, the velocity of the skateboard must be smaller than v ball, okay? Because the ball is thrown with a large speed, but the recoil speed from the throw of the ball is going to be small. Okay, this was question 11. I hope this makes sense. By the way, guys, I noticed that many people watch my videos without subscribing, so it's, I don't know, it doesn't bring me any monetary compensation yet, I mean, this channel, but getting subscribers kind of boosts your ego, I guess, or maybe it helps you mentally to keep going, to keep doing this. So guys, please subscribe, okay? And as always, if you still have any questions on what I teach here, you can ask in the comments, and I always reply. I mean, you can check that I reply to the comments. All right, this was not that bad, right? Question 11. Let's see question 12. Machines make work easier by changing the size or direction of a force. A student designed a simple machine to lift a box of mass 50 kilograms. The student claimed the efficiency of the machine was greater than 90%. The machine used a slope of height 2 meters and length 15 meters to move the box. The box was connected to an 8 kilograms mass by a rope over a pulley as shown. As the 8 kilograms mass fell, the box moved up the slope at a steady speed. Okay. Is this useful, the steady speed? We'll see. So, determine whether the maximum efficiency of the machine was greater than 90 degrees. Okay, so first of all, let's start with the definition of efficiency. So efficiency, and I think you can check the back of the paper and they provide this definition, I believe. Yes, it's over here. So we can read it off. Efficiency is useful energy output over total energy input. So let's go back and see how this will work out for this problem. So useful output energy over input energy. Okay, now the input energy is just M is actually, if we name this capital M, the 50 kilogram mass, and lowercase m is the 8 kilograms mass, then the input energy, right, is equal to mg, and let's call this h, the 2 meters. So h is 2 meters, and lowercase m is 8 kilograms. So mgh is the input energy, right? Because as this mass falls by 2 meters, it pulls the 50 kilograms up by 2 meters as well, right? Because this is a rope there is a rope connecting the two masses. So if the smaller mass falls for 2 meters, then the big mass will go up with 2 meters. Okay, now there is a complication here. So remember that, okay, the useful energy is whatever this component of the force is, we will see, times 2 meters, because if the small mass falls for 2 meters, then the big mass will go up by 2 meters. So actually we have to do some work here to figure out what's going on there. So let me erase something so I can work. So okay, so the weight of this mass is m times g, right? And it can be analyzed into a component, let's use red, in this direction, which is cancelled by the reaction force, and a component along the rope, okay, which is what concerns us in this case. So, and this is actually the useful energy. So whatever this component is times 2 meters. Okay, now that component is, let's call this angle theta, right? So now sine theta, actually I'm going to use a clean page. Sine theta is 2/15, okay? So why is it 2/15? Because the opposite side is 2 meters and the hypotenuse is 15 meters. So now if that angle is theta, then the other angle that is theta is this angle in there. I crammed everything and it's difficult for you guys to see. So let me try again. So this is m times g, and now this component is cancelled by that component, but this angle there is theta. Why? Because this side is perpendicular to this side, and then this side is perpendicular to this side. This side is perpendicular to this side. So if this angle is theta, that angle is also theta, and this component is mg sine of theta, right? Okay, so the useful energy then, actually, let's call this capital M. I'm sorry about being all over the place today. And also I'm a little bit sick, if you can hear it. Okay, so mg sine theta. So the useful energy is mg sine theta. We can remove now the question mark. Mg sine theta times h. And the reason why it's h, again, is because the rope only falls for 2 meters. So it will go up, not up, it will move along the hypotenuse by 2 meters, okay? So let's divide these two. So efficiency is then capital M gh sine theta over mgh, which is the input. So g goes away, h goes away. So we have these nice simplifications. So the mass is 50, sine theta is 2/15, and then little m is 8. So this is 100 by 120 actually, right? If you multiply. So which is 5/6. So the efficiency is 0.8333 or 83.3%, which is less than 90%. So whoever said that the efficiency is 90% is wrong, okay? The student, okay, so the student is wrong. So we can write this down. Student is wrong. Okay, now question 13. A swimmer swims a 100 meters race. A simplified displacement time graph for the swimmer is shown. Okay. Draw a corresponding velocity time graph for the motion of the swimmer on the axis below. Show all work in the space below. They mean this space, I guess. Okay. So the gradient of this graph gives you the velocity, okay? So we will assume that this is a straight line. We can use this point, maybe. So let's see. We can take any 2 points, by the way, on this graph. So this point and this point, or you can take, I don't know, this point and this point, whatever works, okay? Because it's a straight line. So we can take actually this point over there. Okay, so and then this. So the gradient of this part is the velocity in the first part. Okay, so gradient, let's call it 1, is displacement, so over time. So that's 30 meters over, let's see, this is so every little square is 2, right? So 20, 22, 24, 26. So over 26. I'm actually doing this on the fly because I worked it out on a piece of paper and my calculation is not accurate, I guess. So I have to use my calculator. 30 over 26 yields 1.15. Okay, so 1.15 meters per second. And the second gradient, let's call it gradient 2. Let's take this point over there. Okay. Okay, it's gonna be 30 again because it's the same, I guess. And then the time elapsed is 64 minus 90, right? Because this point over there is 64. You can check for yourselves. So if we do this calculation, I think we're going to get something very, very close, if not the same. Minus 1.15, so exactly the same. Minus 1.15 meters per second. All right, so if we come down to this graph now that has velocity in meters per second in the vertical, and at this point, by the way, that the velocity changes is at, let's say, 42, 44, between 44 and 46. So we'll figure it out. So let's call this 0.5, let's call this 1, and let's call this 1.5. I'm talking about these 3 points. And then this, that, and that's minus 1.5. So that's okay. So okay, 1.15 will be somewhere there. Okay. And we said 46, so 42, 44. So we have a line that ends around there. So straight line because the constant speed, right? And then minus 1.15 will be the same. So on the opposite, so something like that, up all the way to 90. Okay, so this is the velocity. All right. Next questions. B. Okay, to increase her initial speed, the swimmer began the race by gliding underwater for 15 meters and then began to use her arms and legs. This was not represented on the simplified displacement time graph. Sketch the axis below to show the actual variation of displacement with time for the first 15 meters of the race. So let me think. So okay. I have a feeling I made a mistake. Let's go back to this. I guess there should be, okay, I'm sorry for returning back, but there should be something like a continuous line, right? So the velocity drops to 0 and then you have to connect the graph like that. Okay, it doesn't work. Let me see. Something like that. Okay. All right, this makes more sense to me now. Okay. Now, sorry, it was in my head. Now, let's go back to this. So, because she's moving much faster if she's gliding, then we don't have a linear displacement. So, in the graph they gave us, we have something like this, right? But in reality, the swimmer moves much faster. So, she is going to do something like this kind of motion. So initially she's gonna gain a lot of distance, but eventually it's gonna fall off and be linear. So beyond this point it's gonna be linear, okay? Something like that. Okay, question 2, part B, part 2. Explain one other way in which the motion of the swimmer has been simplified when drawing the displacement time graph. So I guess the velocity in in the 2 segments of the race is equal which is a simplification, okay, as the student might get tired in the second segment. Okay. Question 14 now. A firework is launched into the air and explodes once it reaches a maximum height. The firework is designed to explode at a maximum height of 350 meters. Show that the vertical component of the velocity at launch is about 80 meters per second. Okay, so this is the Suvat equation. I mean, this is an application of the Suvat equations, right? And we are given the initial velocity, sort of. I mean, we have to calculate it, but we are told what we are expected to find and a distance, okay? So the best equation to use is something that involves distance and velocities and acceleration in this case, and the acceleration is g in this case, right? So we can use v squared equals u squared plus 2as, okay? So the velocity, the final velocity, once the firework explodes is 0, right? Because it stops moving up there. And also we have 0 equals to u squared minus 2gs, where s is 350 meters. And a is minus g because the firework moves up, and g, the acceleration, is minus g downwards in the opposite direction, right? So all we have to do is to calculate the square root 2gs, which is the square root of 2 times 9.81 times 350. So 82.87 meters per second, which is 80 meters per second. Okay, that's the answer. Part 2, the vertical component of the velocity at launch depends on both the initial velocity of the firework and theta, the angle between the initial velocity and the horizontal. Sketch a graph showing how the initial velocity required for the firework to reach the maximum height of 350 meters varies with theta for the firework. Okay, this was a little bit incomprehensible to me in the beginning. So what they are saying is that, okay, in the problem we solved in part A, part 1, we assumed that the velocity, the initial velocity v naught, let's call it u because it's the initial velocity. So the initial velocity u is pointing upwards. I mean, the angle it makes with the horizontal is 90 degrees. So they are asking what's going to happen if the initial velocity is like that, u, and it makes an angle theta with the horizontal. Remember, we still care about the vertical motion. So in the vertical direction, the component is u sine theta, and in the horizontal is u cosine theta, and we don't care about that component. We only care about this one, okay? So in order, though, for the firework to make it up to 350 meters of height, maybe I should write this down, in order for the firework to travel 350 meters upward, the vertical component upward, maybe I can write it like this, u sine theta must be 80 at least, right? So u, the initial velocity, is equal to 80 over sine theta. Okay, I hope this makes sense. So if we plug in numbers, let me help you. If theta is 90 degrees, right, u is 80. If theta is 30 degrees, u must be 160. If theta is 10 degrees, u must be 460. Okay, I hope this makes sense now. So the more the angle between, the smaller the angle between the initial velocity and the horizontal, the more that initial velocity should be in order for the firework to make it all the way to 350 meters up, right? And if theta is 0, then u is infinity, which is okay. It's just for fun, okay? This is, you don't need this part. So if we go back to this graph, if this is 90, we can write that this is 80, okay? And it's in meters per second, right? And then, okay, if that's 90, maybe that's 60, maybe that's 30, and maybe that's 10. So for 30, we found that we need 160, right? And for 10, we found that we need 460, which is going to be, I don't know, maybe up there, okay? So 10. So if we connect these points, so this point, and this point, we find a graph that looks like this. Okay, so this is what they are asking. It's kind of complicated for kids, high school kids, but they can ask you hard questions, right? Some of you guys are gonna go study at Cambridge and Oxford, so while I feel for you, I also don't feel for you. I mean, okay, you have to prove your worth, I guess, I don't know. But this was a little bit of a difficult problem, I think, and this test overall was difficult. And as I was solving this, I realized that, okay, I lived for part of my life in Chicago, which is famous for its skyscrapers, okay? And even the lower ones, like the Hancock's Tower, right? That's how it's called. I think it's 350 meters. So if you're throwing fireworks in Chicago, you have to be careful with the height, I guess, because yeah, it can damage buildings. Okay. Part B, a student wanted to estimate the maximum diameter of the firework after exploding. The student estimated the time taken between seeing the firework explode and hearing the firework explode. The angle phi from the top to the bottom of the firework. Okay, so this is also another complicated question. I don't know, this test was difficult, guys, but what they mean here is, okay, they are giving you this scheme that kind of helps. So if we call this distance, let's call it S, okay? S can be calculated by the speed of sound times the time of delay. Okay, and why is that? The light travels almost instantaneously, right? Instantaneously. So the delay is due to the sound, okay? Hence, S is V sound times T of delay, and V sound is 340 meters per second. Let me second check this. I'm actually gonna Google it. So speed of silence, no, speed of sound. 343 meters per second. Okay, we said 340, we are good. Okay, so we found S, but notice that now we have this right triangle here, okay? So this and this make a triangle, right? So, and this is phi over 2, okay? And this is going to be, let's call this d over 2, the diameter. So sine of, tangent, not sine, So tangent of phi over 2 is equal to d over 2 over s. Okay? And this is the answer. This is what they are asking. Describe how the student could determine the maximum diameter of the exploded firework using the estimated data. Okay, so we have the speed of sound, the time of the delay, and we know phi, so we can calculate it. Okay, it's a weird problem, but I hope it makes sense. Question 15 now. They also made it look scary. So, muscles move body parts by contracting and relaxing. For the forearm to hold the ball in the position shown, the biceps muscle contracts, creating a tension T in the muscle as shown. Okay, a student modeled the forces on the forearm using a uniform beam and spring arrangement as shown below. The length and weight of the beam were the same as the length and weight of the forearm. All right, so we have this diagram. A, it can be assumed that the biceps muscle acts as a spring at an angle of 70 degrees to the beam 4 centimeters from the pivot O. Determine the magnitude of T. You will need to estimate the total length of the forearm and hand. The force of ball on beam is 4.5 newtons and the weight of beam is 15 newtons. Okay, so first of all, let's start with the length L of the forearm. We can estimate it as about 0.4 meters, say, and the length of the hand we can estimate as about 0.15 meters, something like that. So clockwise moments, this is how we're going to solve it. Okay, we are going to take the clockwise moments over O to get rid of this force. I mean, we're not going to use it because you are taking moments against O, okay? We don't know that force, so we take moments from that pivot point, okay? So let me write that the clockwise moments about O must equal the clockwise moments, the counterclockwise, I'm sorry. The counterclockwise moments about O. All right, so if we go back to this, what are the forces that we have, that we need actually? So T is under 70 degrees, so we have to analyze it into this component, which is T sine 70 degrees. The T cosine 60, so there is also this component, T cosine 70 degrees, but it points at O, so it doesn't create a moment, okay? So we don't need that. And we also now have the weight of the beam and the force of ball. Okay, these are given, so we don't need to worry about those. So let's go apply the principle of moments. I'm going to use a clean page. So pretty much we have that T sine 70 times 0.04. Okay, how do I know all this? Because, by the way, T sine 70 times 4 centimeters or 0.04 minutes is the only counterclockwise moment because the other moments are clockwise, okay? So this must equal the clockwise moments. So the weight times the length of the forearm plus the length of the hand, which is 0.55 meters over 2, right? Because we chose 0.4 meters and 0.15 for the hand, so 0.55 overall. And we take the weight as acting from the center, right? Plus F ball times 0.55 minus 0.09 because we are given this distance there. Okay, so this is one of the rare cases in which I plug in numbers from the beginning because I think it's the easiest this way. So t times 0.038 is equal to 6.195. So t is approximately 163 newtons. Okay, and this is the answer. Okay, explain part B. Explains a limitation of using the beam to model the forearm. So the forearm is not uniform, not symmetrical. Okay, and the center of gravity is not in the middle. Okay, and this is the answer. Moving on to question 16. A student carried out an experiment to determine the Young modulus of copper. She used the apparatus below to observe the position of a marker as a copper wire extended under increasing applied loads. Describe how the diameter of the wire should have been determined. So the diameter, so use a micrometer. Okay, use a micrometer. That's the first. Take measurements at various orientations or positions and average. Okay, and average. Okay, so this is it. I mean, there's nothing else you can do. So when we say multiple orientations, we mean that if this is the diameter, it's exaggerated. Okay, so you have to put your micrometer there and then take a measurement there and maybe a measurement there and average. And when we say positions, we mean take a measurement there, take a measurement there, take a measurement there in various different positions. Okay, just make sure that it's uniform. All right, part B. The student calculated the extension of the copper wire for each applied load. She then plotted a graph of load against extension. Okay, so load against extension is F versus X. Okay, so it's a little bit different from the elasticity curves that we use in Young's modulus, but we'll see how to get the result we need. I told you this paper was difficult. I don't know why they made it so difficult. So, okay, so determine a value for the Young modulus of copper. We are given the original length of the copper wire and the diameter. So, let's start with the definition. So, stress is force per cross-sectional area, so pi r squared, and extension, strain, not extension, is equal to delta x, which is extension, over the total length. Okay, so sigma is E times E, the Young's modulus. So the Young's modulus is sigma over the strain, or I'm going to use a clean page. So E is sigma over the strain, or force over pi r squared over delta x over L. So this is F over delta x times L over pi r squared. Okay, you can check for yourselves. And what is this? Is the gradient, that's the gradient of our graph, right? So that's the gradient, because we are given F versus delta x. So the gradient is F over delta x, right? Which is exactly that. So the Young's modulus is going to be E times, E is equal to, so the Young's modulus is equal to the gradient, times L over pi r squared. And if we go back, we can easily calculate it. We calculate the gradient, so I always favor straight lines. So, okay. So that's 6. So the gradient is 6 newtons over whatever that is, 2.6, maybe 2.7 times 10 to the negative 3. Okay, and if we go over there, we find 6 over 2.7 times 10 to the negative 3, which is the gradient times the length, which is 2.4 meters, and then over pi times 1.15 times 10 to the negative 4 squared, or 1.28 times 10 to the 11 pascals, which is the answer for the Young's modulus. Okay. Part C, explain why the sample wire used in the experiment should be long and thin. Okay, so if we use the formula we just found, so if we use this formula, if we use E is equal to F over delta X times L over pi r squared and solve for delta X, and I discussed this in one of my videos. So delta X is F times L over E, which is the Young's modulus, times pi, which is a constant, times wait, I'm confused now, times delta X times r squared in the denominator, or in other words, delta X is proportional to F times L over delta X. Sorry, what did I do? Delta X is not there. Okay, I'm sorry. Over r squared. Okay, this is what I wanted to say. So I'm gonna go back to the clean page. So do I have, why do they, yeah, we don't need that. So can we delete this? Clear, no, not clear. Move page to trash. Okay, so part C is over here. So if L is longer, then delta X increases. Okay, if R decreases, then delta X also increases. Okay, so this is why a long and thin wire are better. Okay, also a small load, a small f, can be used if the wire is long and thin. Okay, additionally, so if the wire is longer, delta X is longer, so it's easier to measure, right? And if the radius is smaller, delta X is larger, so we can measure the delta X easier. And also, if delta X increases, the percentage uncertainty in delta X decreases. Okay, so these are the reasons why we use a long and thin wire. Okay, now let's move on to question 17. Okay, so the diagram shows a climber on a rope face. A rope is kept firmly anchored by a person on the ground and passes through a smooth loop to the climber. The climber slips and falls a short distance as shown. The fall factor is used by climbers to estimate the severity of a climbing fall, and it's given by that. So the fall factor is equal to the height fallen before the rope begins to stretch by the total unstretched length of rope. A climber slips and falls with a fall factor of 0.8 before coming to rest. The energy from the fall is absorbed by the climbing rope, the maximum strain in the rope is 9%. I show that the maximum force acting on the climber due to the rope is about 10,000 newtons. Assume the extension of the rope is proportional to its tension, So the total unstretched length of rope is 15 meters and the mass of the climber is 71 kilograms. Okay, this is quite something. This is quite a problem. Okay, so let's start with the strain, which is delta x over L. So delta x is equal to the strain times the unstretched length. So 9%, 9 over 100 times 15. So 1.35 meters is delta x, so it stretches a little bit. All right, the fall factor. So you see, this is the type of problems they give you sometimes at the A levels. Okay, this is an AS level test, but they just want to test sometimes common sense, because I mean, this is not something you are taught, but you can still figure it out using the information given. Okay, so the fall factor is equal to, as it's stated, the height fallen, so h, which you don't know, over the unstretched length over L, right? So the height fallen is therefore 0.8, which is the fall factor given, times the length, which is 15, so 12 meters. Okay, so we have two pieces of information now. Okay, we can calculate the energy from the fall, which is just the gravitational energy, right? I mean, the guy is falling. So E gravity. So let's call it E gravity is m times g times the height he has fallen, which is h plus delta x, right? Because he falls 12 meters, but the rope stretches for 1.35 meters. So you have to account for that as well. Okay, so combined, that gives us, let me do the calculation really fast. So that gives us 9,298.4 joules. All right. So this energy turns into elastic energy, right? So Eg becomes elastic energy, which is 1/2 F, the tension that we are trying to find, times delta X, right? So F, the one we're trying to find, let's use a clean page. I hope this makes sense. Maybe I will write it in words. No, I think it's clear, right? So we have all this gravitational energy that has to be converted into elastic energy in the rope, right? And elastic energy is given by 1/2 times the force times delta X, okay? So F is, what is it, 2 times E gravity, this is how we called it, over, let me see, over delta X, or 2 times 9298, so 9,248.4 over 1.35. This yields 13,775.4 joules. Sorry, newtons, not joules. This is a force. I'm sorry. Okay, which is, okay, it's much larger than 10,000 newtons, but it's about that. Okay, so this is the answer. Okay, part 2. A new climber suggests using a longer length of rope between the loop and the climber, as this will absorb more energy after a fall. Comment on this suggestion. Okay, the problem is that it's going to fall at a higher height, will have a higher velocity. It's actually, we will need a lot of force to stop it, so it's not a good idea. So the climber would fall a higher height, a higher h, and hence reach a higher velocity. So a much larger force from the rope will be required. Okay, so not a good idea. Okay, part B, climbing for okay, into my notes. Climbing rope manufacturers recommend that ropes are replaced every 5 years. The force extension graphs up to the breaking point for a 1 meter length of rope when new and wait, what am I saying? Climbing rope manufacturers recommend that ropes are replaced every 5 years. The force extension graphs up to the breaking point for a 1 meter length of a rope when new and after 5 years are shown. All right. Comment on the manufacturer's recommendation. Your answer should include calculations. Okay, so the stored energy is equal to the area under the graph. Okay, so this is a tedious problem in that you have to calculate. So for the new rope, the area under the graph is this region. Okay, so this is the area under the graph. Okay, so for the new rope, we approximate the area as 1/2, like it's a triangle, which is not, but okay, I was kind of feeling lazy, times 0.135, which is, let me see, which is the end of this graph, okay, times 17,500. Wait, what am I saying? No, this is not gonna work. I mean, okay, you can approximate it as a triangle, but okay, it's more appropriate. I just saw that I actually did it to count squares. Okay, so count these small squares. Okay, so this square over here. Okay, so if you count the squares, you will find 1, 2, 3, 4, 5, 6, 7, and then these two can count as 1, 8, and then this and that count as 1, 9, and then maybe 10. Actually, I found 12 when I did it. So let's say that for the new rope, we have about 12 squares, which is approximately equal to 12 times 0.0025, which is the area of times 2,500, and this is the area of the small square. Okay, so that's about 750 joules. And if you do the same for the old rope, so you have to calculate the area under this graph. Okay, so you have to count squares again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10, 11, something like that. Okay, so you actually find, so old rope, about 9 squares. So 9 times 0.025 times 2,500 yields 763 joules. So the old rope absorbs less energy. Okay, and also okay, for the same force, okay, K of the new rope is larger than K prime of the old rope. Okay, and even though it's not asked, you can actually calculate. Let's use orange. So if we use 10,000, if we use the 10,000 newtons, okay, the constant of the spring will be tangent to this point at 10,000. So the gradient of this line that I'm drawing, okay, so this gradient is equal to K, and we use 10,000, okay, and if we come here to the old rope, we see that the tangent is less steep, okay, so the gradient, so gradient prime is K prime, and we see that K is larger than K prime, okay. I hope this makes sense. This was another complicated problem in this test. I don't know why they did this to kids back in 2019. It was before COVID, by the way. It was a bad year for me, actually, because I left the United States. I don't know, it was a tough period for me, changing jobs. I moved from the US back home, but I don't like it really back home, and I miss the US, and I don't know, it's a mess. So it was a bad year. So anyway, let's go to question 18. Okay, let's see. Okay, before we jump to part A, let's read it. When water vapor in the atmosphere cools, it condenses, forming tiny drops of water. These drops increase in size by colliding with each other and fall back to the ground as rain. As a raindrop falls through the air, it eventually reaches its terminal velocity. The upthrust on the raindrop can be considered to be negligible. Okay, explain what is meant by the terminal velocity of the raindrop. Your answer should include a free body diagram for the raindrop when terminal velocity has been reached. So, terminal velocity means that the body is moving, but the acceleration becomes zero, okay, which means that there are two forces that are equal acting on it. So the first force is the weight. So that's the weight, and then the drag force should be about the same. Okay, so the drag force, drag. Okay, so terminal velocity is reached. Okay, when the sum of all forces is zero, which means that A is zero. And in other words, drag is equal to the weight. Okay, in that case, the drop stops accelerating. Okay, reaches its highest velocity. Okay, velocity, which it maintains. Since no more acceleration is acting on it, it maintains that terminal velocity. Okay. Okay, I mean this is it. Okay. Part 2. The air resistance F acting on a raindrop traveling at a velocity v can be determined using the expression, that expression over there. Force is equal to 0.45 times rho times A times v squared. Rho is probably density, A is probably cross-sectional area, and v squared is the velocity. Yes, exactly. So where A is the cross-sectional area of the raindrop and rho is the density of air. Calculate the terminal velocity of a spherical raindrop of radius 2 times 10 to the minus 3 meters. They give you the density of air and the density of the rainwater. Okay, so again, when terminal velocity is reached, the weight is equal to the drag force. So weight is equal to force, the drag force. So m times g becomes equal to 0.45 times rho of air times A, let's write it down, times V squared. Now we are not given the mass of the raindrop, but we are given the density. So you can write the density of rainwater. So rho of water, right, times the volume is equal to the mass. So the volume is 4/3 pi r cubed times g, and this is equal to 0.45 times the density of air times the cross-sectional area of the raindrop. Okay, so be careful, not the surface area, the cross-sectional area. Okay, so when we have a raindrop, okay, which is spherical, the cross-sectional area is simply the area of the circle, right? So pi r squared is what we have to use pretty much, right? Times V squared. I hope all this makes sense. We can make some cancellations. Pi goes away, r squared goes away, and we're left with just r. So V squared, notice how I am not plugging in numbers, okay? Rho water over rho air times r times g. Okay, let me think. So V squared is rho water over rho air, and then rho times g times 4, right? I forgot the 4. Okay, over 0.45 times 3. Okay, and now we can do the square root. So V is the square root. Actually, I can plug in numbers now, it's safe. So density, wait, I confused myself for some reason. So let me see. What did I do there? Rho, okay, G, rho water. Something's off. No, it's not off. So okay, so let's plug in numbers. 1 times 10 to the third for the density of water times the radius, which is 2 times 10 to the negative 3, right? Okay, times 9.81 times 4 over 1.2 times 0.45 times 3. Okay, and if we do this calculation, we find 6.96 meters per second. Okay, that's the answer. Part B, some plants, okay, have adapted to high rainfall by having a specialized shape and waxy leaves. This allows rain to slide down a leaf and off the end of as a series of drops. A drop of water slides off a leaf as shown. Add to the diagram to show the position of the drop at regular intervals of time. The first two positions have been drawn for you. Okay, so first of all, in the x direction there is no acceleration, so it keeps moving at constant intervals. So something, and then in the y direction, so what I'm trying to say is that in the x direction, ax is 0 and ay is minus g. And also, okay, it has the drag force, which reduces that g, but whatever, okay, it's accelerating downwards, right? So if this is delta x, okay, so if that's delta x, then the next drop will also be at delta x, but if this is the height it traveled down, it should travel a little bit more, and then again the horizontal distance again should be delta x, and should travel a little bit more. Okay, so this height is larger than the previous one, and then this height is larger than the previous one, and then the next one should be again at the same interval delta x, but further down, something like that. Okay, and that's the answer. Water falls from a leaf at a steady rate of 5 drops per second. At each drop, as each drop reaches the ground, there are 4 drops above it in the air. Calculate the height of the leaf from the ground. It can be assumed that the drop at the highest position has just left the leaf. Okay, so Suvat equations. I mean, there is nothing else we can use, right? So we need a distance. So the best one is S equals to some initial speed times time plus 1/2 AT squared. There is no initial speed, so we can consider it 0. And we can call S to be this h that we look to find. H is 1/2 g t squared. So 1/2 times 9.81 times the time. Okay, 5 drops per second. So 5 drops per second, right? So if we invert that, we have 1/5 seconds per drop. Okay, so the time for the drop, for one drop to fall, is 1/5, right? For one drop. And there are 4 drops, so 4 times 1/5 pretty much. Okay, so the time is 4 times 1/5 squared. Okay, or 3.14 meters. I hope this makes sense. So I'm gonna write it in the back. So 5 drops per second. So 0.2 seconds for one drop is the time taken for one drop to fall. Okay, and we have 4 drops up on top of the last one. So 4 times 0.2 is equal to 0.8 seconds. And this was a very difficult, I have to say, Unit 1 test, past paper for Unit 1. This is the AES level. It's usually year 12 students, but occasionally some year 13 students take it because they want to go to medical school and other reasons. So this was a very difficult Unit 1 from 2019, which was again a very bad year for me because I changed jobs, countries. It wasn't a good idea, but I did it. So yeah, this is it, guys. Thank you. I got a lot of subscribers lately. I hope to get more. I hope to grow this channel into something big. Hopefully introduce new ideas, new concepts, new videos, not necessarily only on AES level, but we'll see how it goes. Please like and subscribe. If you have questions, ask in the comments. I always reply. And see you in the next one. Bye.